mass M. Some people brushed twice a day, three times a day. Some people brushed once. Some people brushed once a week, right? So they're all going to have different amount of deposits of the thorium on their teeth. So we are not prescribing 10 milligrams of thorium here. We are saying what percent of whatever you put up, right? And different people put a different amount, so we're going to call that initial amount of thorium M. And then you're going to put PM on the other side, which is P times M. P stands for percent of initial mass, capital M, which is where these M's drop. And this T is going to be 70 years because these people have been dead for 70 years, right? So we are going to calculate how much is left. So P equals E to the negative 0.0009443 times 70 in the exponent. Again, no calculus there, you just plow through calculation. So I have times 70, and then I have my, then I have E raised to the answer, and that gets me that the P is equal to 0.993. 99.3% of thorium-229 left. After 70 years. 70 years, only 0.7% of thorium decayed from the teeth. The rest is there. These are still the most beautiful corpses we have.
So we can still make some.
You want to go scrape it off, you mean? Okay. So this is what we have for radioactive decay, and some of these elements, I mean, they are highly deadly and toxic to our bodies because, you know, throughout the evolution, they were deep into the ground, right? It's now when we became too smart and started digging them up, right, to make all of the nuclear stuff that we are using. However, we did not come into contact with these elements that were deep into the ground as we were evolving. So we do not have natural resistance, right? We did not evolve to have natural resistance to these things. And then when Chernobyl and the other nuclear issues happen, then we have problems. Also, the reason why we are afraid of nuclear weapons. See, nuclear weapons have multiple strikes. There is the initial uninhabitable because of the high levels of radiation that stay, which is radiation poisoning. And there are, if you're interested, obviously, there are clear websites where you can learn of what are the doses that we can withstand and what are the doses that we cannot withstand. So you can learn about that. So that's thorium. There you go, thorium with the Doramed toothpaste. And now, what can you do with this? Well, a whole bunch of stuff. You can, the limit of this model, you see the model up there. So if you want to do some calc with a capital K, right, you would take the limit as time goes to infinity to calculate the 0.0000443t to calculate the limit as time goes to infinity to calculate how much thorium is going to be there if you wait infinitely long. And the answer to that is obviously 0. It will decay to 0 because all of the exponential decay graphs look like that. Eventually it will show up. So you have to wait infinitely long for the thorium deposits to go away from the teeth, right? So that's not something that, you know, is easy to wait, right? Our expiration date is about 100 years at most, and then that's the end of the road, right? So this is our mass, this is our time, and the mass will go to 0 This might update, might not update. I'm just going to talk now about metabolizing drug in a system, and that will be the last problem to look at. We can talk about, let's say, generally I talk about Advil, but we can go and figure out aspirin. We can figure out technically anything, because we can go on Wolfram Alpha and find the half-life of these drugs. The idea is that when you take medication of any kind, it's not an instant. It's not an instant shot. It takes time for it to go through bloodstream and reach the place where it needs to take the effect. So it's not an immediate relief. Now, those that are immediate relief, they actually just kill your nerve system, because they're okay, no pain right away, right? Yeah, but that's the shock of that. It's not going to be the Advil and all these other things that go to the bloodstream. Right? It takes time for it to go to the system. You take the pill, it has to first go all the way to the stomach, then it gets digested there through the stomach, right? It goes to the intestines, goes into the bloodstream like everything else, like food and other nutrients, and then gets distributed to the body. The half-life of Advil is 1.9 hours, so we'll call that 2 hours. And you know what the bottle says, right? For Advil and all of these medications, you generally 4 hours, and then you take the next dose, right? Well, see, at 4 hours, again, exponential versus linear, right? It's exponential decay. So, is in 4 hours everything gone? If the half-life is 2 hours? No. The answer is, well, you're nice, so you say no. The answer is hell no. Right? Because remember, half-life, which is 2 hours, is going to take away half of the amount. So if you start with 500 milligrams of medication X, and you wait 2 hours, you're going to end up with 250 milligrams left in, and 250 is in the bloodstream doing the work. And then you're going to take another 2 hours, and then you are down to 125 milligrams. But now, how many hours has passed? 4 hours. So what do you do after 4 hours? Yeah, you take another dose of 500, and now your bloodstream has 625 milligrams, right? So you started with 500, and then the 2 hours took it down to 250. That's your new point, right? For the next 2 hours, it's half of that. It's 125 now. And then when you have 125, oh, it's 4 hours. Boom, another one, right? And then your system now has 625. Wait 2 hours, right? It's going to cut that into 2.5 milligrams. So that's after 2 hours. And then you wait another 2 hours, right? And then you see that with every single dose that it's the same level, right? The actual amount in the bloodstream, the actual amount in the body increases, right? Even though you're taking, right? So every single time there's more and more and more and more drug introduced. And it's going to follow the same formula. So we can go and pick up literally anything. You can, generally I work with, I go and I just type Advil, but we can pick up literally any medication and take a look. So let's go to Wolfram Alpha. And take one of these menace things So I should get the half-life maybe for this one I have to pay because it's not listed here. For many others are. Okay. Well, let's go with the one that I know that all the info is there. So what can I do? What? Oh, okay. Here. There it is. So if you take a look at Advil.
That's a lot of Advil to kill you.
Little dose?
What? 1,255 milligrams per kilogram of body weight. Have to be pounding those things down.
Yeah.
Well, that's how much it would take to like kill you from like shock, but like your liver, if your liver shuts down.
Yeah. 1.2 hours. Now, since we're lazy, we're just gonna say 2 hours. All right. And then you can calculate everything the same way. Let me see if they give us info on other things, because I'm kind of sick and tired of doing the same one over and over and over again. No. I don't know what the spelling is. Got it. So for all of these, you get the chemical compound if you want to cook it up at home, and yeah.
You just need the half-life of it?
Yeah, I mean, there are other websites where I could find it. I just wanted to see, but we can work out the same thing. So let's work out our friend Advil over here. Isn't that how close this word Advil is to devil? It's like so close without actually being there. Anyway. What is that? The capsule is 200, 250, 200? I don't know. I don't take it.
There's a range.
There's a range? Of course. All right, so 1 kilogram capsule. 200 milligram capsule or tablet or whatever. Let me see something real quick. Yeah. All right. Well, we'll do the capsule. Okay. Come on, E. There we go. All right. So 200 milligram capsule, and let's do this. How long do we wait for the amount taken to go down to, let's say, 10%, 5%, what should we do? 10% of initial dose. We don't actually need 200 for this calculation, but you already know every time you pick up a bottle, right, of these things, you know how much each capsule is. So we're going to use 2 hours. Well, I don't know. Let's use 1.9. Let's use 1.9, the official value. All right, so what do? We go and take the standard calculation first. We know that the formula is m equals to capital M e to the k t, and then m over 2 is equal to m e to the k lambda. Now your initial dose is the capsule, so it's 200, right? So it's 200 over 2 is equal to 200 e to the 2k, because lambda is 2 hours, right? So I'll just say lambda equals 2 hours. That's given to us in the problem. So now we have the good old ln of 1/2 is equal to ln of e to the 2k. And we have our calculation from before, where we got that the ln was of 1/2 was negative 0.6931 is equal to 2k, from where k is equal to, so ln of 5 divided by 2, negative 0.3466. There we go. And we have our model for Advil now. The mass of Advil in the system is the initial mass, which is 200, right? In this case, 200 tablet, e to the negative 0.3466 t in hours. That's very important now because we are dealing with the medication. It's not going to be thousands of years, like you're not going to make it, right, on the half-life. Good. So now what do you want? You want to have 10% left, right? So 10% of 200 left is how much? 20 milligrams. Good. So the 20 is equal to 100 e negative 0.3466 t, and then t is going to come up in hours. So over here, when you divide, right, you have 10%, so 0.1 is equal to, leave space for ln, and e to the negative 0.3466 t. Put ln on both sides, and now we have ln 0.1 divided by negative 0.3466 is going to be the t we are looking for. So ln of 0.1, close the parenthesis, divide by negative 0.3466, going to give me 6.6. That will, all of that needs to be part, and it will be part forever, cannot be 100%, because we see it from mathematical equations, obviously. Now the amounts are so minuscule, because you can go and compute, right, when it's going to go down to atomic level, right, which is in that case, could be impacting DNA, but the idea is that it should not be, at least we can trace it very well. But mathematically, clearly, right, if the zero hits at infinity, 100 years doesn't matter to the time span of these things.
So would that be why, like, if you're addicted to like opiates, they have like that 2-year like post-acute withdrawal symptom? Is that why?
Oh yeah, definitely. And more of everything else you can compute for any kind of drug, because most of the people who get hooked up to any of the harder drugs, they start with the basic painkiller prescription from a doctor. If you just search internet for 7 seconds, you are going to find the stories of people who OD'd on heroin, and they were sport athletes in high school who got a broken ankle or dislocated shoulder and hooked up on whatever opiate was given for the pain, most of the drug addicts actually today are not the ones who actually seek it out to begin. Some of them will be on a party and let's try this, try that, sure. But the vast majority of them are actually just a doctor prescribed medication that they got hooked on and they couldn't get it after, because they got hooked on it and they couldn't get it afterwards, so they would be buying on the street something that is much more potent and cheaper than what the medication would if you don't have insurance, right? So these are the scary things. And when you are, running the calculation, right, on these things, you see that we just saw. I mean, we all know what the decay model is, right? You have the mathematical decay model. They always look the same. That's the E, right, in time. This is the amount of mass that it's in a system. And this over here is the dose, M, you took. And where is going to be 0? 0 is going to be at infinity. This is, 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, 6 hours, then times the amount of hours in 2 years, right? You have the power to go and say, okay, we are talking about this particular type of opiate, which has this particular type of half-life, which is probably known, right? And then you can go and you can calculate the same thing I did for Advil, except you're going to change the half-life of whatever is there, and then compute down the line of the percentages and all of these kind of things, following the same steps, replacing one number. That's what you're replacing, one number, going down the line to calculate the percent, and then you can see how much is left 2 years later, even though the half-life is measured in hours. When you are talking about something that it's on an atomic or molecular level, right? Avogadro's number comes into place, right? 1 mole of substance is usually a handful of stuff. So if I am to, hold this much iron or this much wood or this much, whatever in my arm, they say handful of stuff is going to be 1 mole, and then 1 mole of matter has
10 to the 26 atoms, particles?
6.022.
6.022 times 10 to the 23, right? So now 6.022 times 10 to the 23. 23. That's, guys, 23 zeros. All right, 23 zeros. That's not the billions are nothing for it. Trillions are nothing for it. This is order of a million more than a trillion. I mean,
Withdraw it.
huh?
Withdraw it.
Go ahead. 23 zeros. You put 6 here. Put 6 and then 23 zeros after it, right? And then go from the back and separate 3 each. So 6. Okay, put 6 0. 6 0 2 2. Number 2. 2 2. Okay, and now put 20 zeros after that. So that's the amount, right? That's the amount of atoms in this much stuff, right? In that much amount of atoms. when you think about it, right? So it's not going to be a lot of it, and you can run the calculations back and see. There we go, and then you have 602. All right, let's hit the break. Bye.